Hello class. Today we're going to be learning about double integrals, but we're going to learn a bit of a hack that's going to help us to do double integrals over certain regions easily, or at least easier. Let's take a look at this double integral. We are looking at integrating over a disk of radius 2. If we consider a disk of radius 2, we know the equation for that is x squared plus y squared equals 4. And then if I'm going to integrate with respect to y first in this integral, I would have to solve for y. So my lower bounds are negative 4 minus x squared under the square root and the square root of 4 minus x squared. Now those can cause very difficult antiderivatives when you go ahead and plug those in. So today we're going to explore using a different coordinate system in order to compute double integrals if the region is circular or circle-like. If we look at the bounds for polar coordinates of a circle of radius 2, theta and r will both have numeric limits. We just have to have theta range from 0 to 2 pi to complete the entire circle. And then we would have r go from 0 to 2 so that we can then fill in the circle, all the radii between 0 and 2. And then that gives us our region. But our bounds are so much easier because they are numeric. The only caveat with changing a coordinate system for an integral or a double integral is that we are going from integrating with respect to y and x in whatever order we want to integrating an integral with respect to r and theta. Because in a rectangular coordinate system, dA equals dy dx or dx dy, because we have all these nice right angles, y times x is the area of those little rectangles that are created, that is a very easy coordination from dA to dx dy. However, dA does not equal dr d theta because we no longer have rectangles. We're rotating theta and we are going out a radius of r. So we're going to need to determine just what dA is under polar coordinates. So let's take a look at this diagram. I am trying to express the region in green. Notice that my theta is going to range from a theta equal to alpha to a theta equal to beta. So I'm going to rotate this from alpha to beta. That gives us these bounds for theta. Then if r is listed in terms of functions, r can also be numeric values as well. The closest radius is going to be represented by h1 of theta. And then the radius further away is going to be represented by h2 of theta. So if we range r between h1 theta and h2 theta, it's going to fill in this space in between the inner and outer radius. And then if I rotate theta from alpha to beta, I'm going to cut off those particular bounds. Now, in order to consider what dA is, we have to consider carving this up because that's what integration is all about, carving up into tiny pieces and then calculating the area with a simpler shape than what we're looking at. So if I carve up that region into smaller pieces, what we have here is just a sample little piece in the region. So we're carving it up into these rectangular-like shapes where we have the radius going from the inner to the outer radius. And so because we're going from the inner to the outer radius, we call that dr, or delta r. So delta r, if we go to calculus from just making increasingly smaller regions or smaller changes in radii, is also dr when we apply it to the calculus. Then when we look at our other side is r times theta. So what we have learned over the years is that r times theta, as long as theta is in radians, it equals s. And s we use to represent arc length. So arc length, it's no surprise that that's going to be an arc length there because it is the arc as it sweeps across that region. So it's basically s times the change in radius there. And so that is what calculates the area of all these little almost rectangles. They become actual rectangles the smaller and smaller and smaller they get, because the smaller the little piece is, the more straight that edge is going to be. So now what I look at is that the area of each of those little pieces is found by doing S, here S is, times the change in radius. Okay. So our area is S times R, or S, which is the arc length, times just the change in radius. Now we know we can take this from a lens of carving up infinitely small little rectangular-like pieces to calculus if we do an infinite number of those little pieces. And so if we go to infinity, we can say that d theta equals delta theta, and dr is approximately equal to delta r. And then we can do a substitution that dA being approximately delta area, the change in area. So dA is r dr d theta. And that is what we're going to use when we do a change of coordinates to accomplish a double integral, if it's easier to do it in polar. So this is the main idea for doing the coordinate change, is that we can't just say dA is dr d theta. It is not. dA is r dr d theta. Other tools which will help us convert to polar coordinates, these we talked about earlier this year. You also talked about it last year. We have that x equals r cosine theta, y equals r sine theta, and as always, x squared plus y squared is r squared. So in order to do a change of coordinates from Cartesian to polar, you have to convert your function so that it is a function in terms of r and theta. So that's the function conversion. And you also have to convert the coordinate systems. dA is now r dr d theta. So that's converting the variable of integration piece of it. And then, as always, you have to have different bounds. So the bounds are going to be the bounds of theta, or the bounds of r, and then the bounds of theta right here. Okay. So basically 3 different changes we need to make to the integral. We need to convert the surface to polar coordinates, so using r and theta. We need to convert dA to r dr d theta, and then of course the bounds will change because the variables have changed. Let's do a problem. We have our integrand with respect to area, double integral, and the region that we are going to integrate over are basically just 2 circles that are to the left of the y-axis. So that means we're not going all the way from 0 to 2 pi. So the inner circle has a radius of 1. just our classic unit circle. The outer circle has a radius of radical 2. It looks like I'm drawing all of it. I really shouldn't draw all of it because it just says it's to the left of the y-axis. So I'm just going to go ahead and erase so I have everything to the left of the y-axis. So here is my graph. In anticipation of integrating with polar coordinates, what I'm going to do is find the boundaries. I'm just going to shade in what this area that we're integrating over is. And so I think we can see that r is going to range from 1 to radical 2. And then theta is going to range from pi halves to 3 pi over 2. So that gives us our bounds. Now we know dA is r dr d theta. We also know that x plus y is r cosine theta plus r sine theta. So I just wrote out that particular substitution there, going from Cartesian to polar coordinates. So I think we are ready. Let's do the thing. It is the double integral r cosine theta plus r sine theta, r dr d theta. Since I have dr first, I need to put those boundaries on the inside. Theta, we have pi halves to 3 pi over 2. So there we have it. That's our integrand now converted to polar coordinates. This is kind of cool because I can use my integration trick to, instead of doing one double integral, which indicates like you do the inner and then the outer, work our way out, I'm going to write this as a product of 2 single integrals because this is factorable. I can factor the r from the thetas. So I'm going to do that. The thetas, I'm going to gather all together. The thetas are cosine theta plus sine theta d theta. And then everything having to do with an r, I have the r bounds. And then if I factor an r out of each of these, I have an r on the outside. So I get r squared dr. So again, I could have done this as one double integral. However, I tend to like to separate if I can because it just feels cleaner. So now I'm going to integrate this one. I get sine theta minus cosine theta going from pi halves to 3 pi over 2. So what I get at 3 pi over 2 is -1 minus one. Oh no, sorry, I'm doing cosine. I just got lost. Here I found myself. And then minus 1 minus 0. So -2 is the result of integrating all the variables in the bounds related to theta. Now let's do r. So I get r cubed over 3 from 1 to radical 2. So I get 2 radical 2, that's 2 radical 2, or radical 2 cubed, over 3 minus 1/3. So that's what I get evaluating the pink integral, the ones with all the r's. Okay, so finally let's bring it together. It is the product. So it is -2 times the following, 2 radical 2 minus 1 all over 3. So if I want to simplify, I get 2 minus 4 radical 2 all over 3. So fun. Love it. There it is. Hopefully you can follow that work. But the regions would have been pretty terrible. You know, the inner and the outer. So I love that we get to go to numeric bounds. Let's look at another one. Oof, I would definitely not want to do this with Cartesian coordinates because you can't take that integral. Like you don't have, if your u is x squared plus y squared, you don't have a du. So that would be tricky. Also, our bounds are curvy. So let's do the unit circle. So that one has a pretty straightforward. Our radius is going to go from 0 to 1. And since it's the entire unit circle, it's 0 to 2 pi for our theta. So that's what allows us to color in this circle. Then if we look at our integrand, it's going to be e to the r squared because x squared plus y squared equals r squared. And then dA is r dr d theta. Pretty fun. And then our r is 0 to 1. Our d theta is 0 to 2 pi. I would like to separate this as well. I'm going to go for it because I just feel like it really cleans up the double integral. If we're talking d theta, I'm going to go 0 to 2 pi d theta. That's going to be nice and straightforward. And now let's do times 0 to 1 e to the r squared r dr. So I'll do the very simple one first. This is just 2 pi because you get theta evaluated from 0 to 2 pi. So that just leaves a 2 pi. Let's look at the blue one. I have a u. This is the u. I need a du. My du would be 2r. So what I'm going to do is multiply this by 2 and then throw a 1/2 on the outside just to keep the integral equivalent. So what I essentially have here is e to the u du times 1/2. So now when I take the integral, it's just e to the u. And then over, well, let me write what it is instead of u. We know what u is. It's r squared. So e to the r squared times 1/2. So over 2. And I'm evaluating that from 0 to 1. So what I get is e to the 1 minus e to the 0, which is 1, over 2. Because it's essentially e to the 1 over 2 minus 1/2. So I'll just write that as a complete fraction. And I have to multiply these two together. So what I get is 2 pi times e minus 1 over 2. So I get a fun little answer. I get e pi minus pi. Because the 2's cancel, I'll just distribute that pi. Why not? And if I were to try to do this with rectangular coordinates, it would not have gone well for me. I would have, I don't know what I would have done. So that's a much better choice. All right, we have our last example here. It's a little trickier because we're not just given an integral. We have to write our integral. So it says determine the volume of the region that lies under the sphere centered at the origin, radius 3, and above the plane z equals 0, and inside the cylinder, x squared plus y squared equals 5. That would be a circular cylinder. So keep in mind that volume is the double integral of f dA. That gives you the volume. So since this is a sphere right here, I am going to need to solve for z so that I can have an f of xy. So solving for z, I get z equals the square root of 9 minus x squared minus y squared. Typically, I would have to do plus minus, but it says it is above the plane z equals 0, so we're not going into negative z's, so we're not going to consider a plus minus. When I look at kind of what this thing looks like, here's the xy plane, here is z. You essentially have a sphere, 1, 2, 3, 1, 2, 3, a half sphere, a semi-sphere, if you will. I'm really going to try and draw this. I don't know if this is a great idea. No. Maybe, no, I don't like it. Sphere, let's think circular. I feel like it might be getting worse. I don't like it. Let me try one more time. I'm going to pull this together. It's going to be great. Let's do it. I'm going to do some negative x, negative y, and then I don't know what I'm doing here. Yay. Okay. That's not terrible. But then we're going to have to throw a cylinder inside of a sphere, and the cylinder has radius square root 5. So like here, we're just going to do a cylinder. And then it has a domey top. Okay, so picture this. Something like that. That the sphere is on the top, and then it has a cylinder, and then it stops at z equals 0. So that's what we're going for. I do have a photo right here, so we can kind of get a sense of what it looks like, but I was trying to recreate that. Yeah, not great, but I think we can all picture it now. So my integrand is z equals the square root of 9 minus x squared minus y squared. I think it's clear that we're going to want to go to cylindrical coordinates. So it's going to be z equals the square root of 9 minus r squared. So that is our integrand. That is our f of xy, which is now converted to polar coordinates. If we look at the r value, because we're inside a cylinder, in terms of our bounds, we're inside of this cylinder. So that means our r values, to color it in, are going to go 0 to square root 5. And because it's the entire area inside of the cylinder, we are going to try and go 0 to 2 pi for theta. So I have my bounds in cylindrical. I have my integrand. And we know it's r dr d theta. So I'm going to set it up. So r goes 0 to square root 5, theta goes 0 to 2 pi. My integrand is the square root of 9 minus r squared, r dr d theta. And there it is. Okay, so let's take this integral. So I have, like, if my u here is 9 minus r squared, ooh, I can separate this. Sorry, very excited to do that. Let me just separate it out. I'll put my 0 to 2 pi d theta right there. And then let's just do the r's. 0 to radical 5. I'm going to put the r out front, r square root 9 minus r squared dr. And if I call the inside of this u, I almost have a du. You know, if we think of integrating by substitution. What I need it to be is negative 2r. So I'm going to multiply this by negative 2, so I have a du, negative 2r, And then on the outside, I'll put that negative 1/2 to just make it an equivalent integral. So this is essentially u to the 1/2 du, the integral. And so now we can take that integral, and what I get is 2/3 times 9 minus r squared to the 3/2. And then I have that times negative 1/2 from the negative 1/2 I had to multiply on the outside of the integral just to account for getting that du to be negative 2r. So I have negative 1/2 times 2/3 because we need those powers to cancel if we were to differentiate. And then we are doing r from 0 to pi halves. Sorry, to radical 5. So this is going to be super fun. Negative 1/3 because the 2's cancel. 9 minus 5 is 4, so it's 4 to the 3/2 power. And then it is plus 1/3 times 9 to the 3/2 power. So let's do this math. This is negative 1/3, 4 to the 3/2 power. Take the square root of 4 is 2, so that's negative 8/3, plus the square root of 3, 27/3, so 19/3. So that's the r portion of it. And then the theta portion of it is just 2 pi. I'll do this a little more specifically because I know the last one I rushed through it. The integral d theta, 1 d theta is just theta, and theta evaluated 0 to 2 pi is just 2 pi. So what we have is 2 pi times 19/3. So what I get is 38 pi over 3. So again, this one was a great candidate for polar because number one, you had all of these curvy things, you had a sphere, you had a cylinder, and so it just set you up for success with all of that. Here's the picture I showed you, and here's your assignment. Enjoy.